So let's start. This is week 9 of Physico Chemical processes for wastewater treatment, and this is online live session for the course offered by Professor V.C. Srivastava from IIT Roorkee, and I am the TA for this course. I am Vaibhav Kabadwal. I am a PhD scholar from IIT Madras from the Department of Civil Engineering, and my discipline is environmental engineering. So this is the lecture outline. So today we will discuss about membrane process. So let's start. So membrane process is a gas-driven process. It's a pressure-driven process actually. It's a pressure-driven process because we apply pressure, and it's not gravitational because more force is required, not temperature, not concentration. It's a pressure-driven process, but we need to apply force so that the water can pass through the pores of the membrane. What is the operating pore size for microfiltration process? So here we have uh, pore size for microfiltration. So for microfiltration, it has a size of greater than 50 nanometer. Next question is, what is the operating pore size for reverse osmosis process? So the operating pore size for reverse osmosis is very less. It is a highly efficient membrane process, and it has pore size less than 2 nanometer, and it requires more pressure, more pressure, more pressure required. So RO, we have RO, we have nanofiltration, we have ultrafiltration, we have what did we study in the last? Microfiltration. Pure water transport across a clean porous membrane is directly proportional to the dash, and inversely proportional to the dynamic viscosity. Pure water transport across a clean porous membrane is directly proportional to the. So in this case, it is asking like this is the membrane. It has pores. So the pore water transport, the transport which is going on through the membrane across a clean porous membrane is directly proportional to the concentration of ions, transmembrane pressure, color of the solution, temperature. This cannot be the answer. Concentration of ions is also wrong. So for in this case it is transmembrane pressure. So more the pressure we apply, so more transport will happen. Directly proportional to transport. Clean porous membrane. The unit of dynamic viscosity is. The unit of dynamic viscosity is Newton second per meter square. We can write it as Pascal second. So Pascal is nothing but unit of force, that is Newton per meter square. That's it. So the answer is Pascal second. The unit of tortuosity factor used for the calculation of force in commercial water treatment membrane is. So the tortuosity factor is tau. It is dimensionless actually. So the answer is D. Which of the following is correct correlation that describes the change in viscosity due to change in the water temperature? So if we change the temperature, we know the viscosity will change. So if the viscosity will change, we have a formula here. So the formula here is described as mu is equals to 1.777 minus 0.052 T plus 6.25 into 10 to the power minus 4 T square. So this is the formula. So the answer is A. Here T is temperature in degrees Celsius. The liquid containing the retained constituents is known as the liquid containing the retained constituent is known as the permeate is which will pass. Permeate is which will pass after filtration, let's say. Heat stream is influent. Product phase is like this, it is kind of permeate only. Retained phase is the liquid containing retained constituents. So it is the answer is retained phase. What is the membrane in water or wastewater filtration? So the question is, what is membrane? So here we have defined the definition of membrane. So membrane is nothing but a thin layer of material that is capable of separating materials as a function of their physical and chemical properties when a driving force is applied across the membranes. So this is membrane. This is about membrane. So it is highly permeable to some constituents and less permeable to others. It is highly permeable to some constituents but less permeable to others. This is the property of a membrane. What are the different inputs and outputs into and from the membrane filtration process? So what are the inputs and outputs? Let's see it here. So we have here one membrane. So this is feed in, this is feed stream. So this is the membrane here. First of all, this is the membrane. This is the membrane and this is the feed stream. Feed stream. This is the product stream. This is the product stream. The product stream. This is the product stream. And this is the reject or concentrate. Reject or concentrate. So we have here feed stream. This is feed stream. This is the product stream. After filtration, this is the product stream. And third one is a reject or concentrate. So this is called waste stream containing particulate matter. So the particulates which are retained from the membrane that will go through the reject. So these are the different inputs and outputs. Which membrane is used to separate ions from solution? Ions are very small. Ions are very small. So for that we need very fine pore dia. We need very fine pore diameter. So which membrane, like we have studied, we know about reverse osmosis, nanofiltration, ultrafiltration, ultrafiltration and microfiltration. So out of these four, which one is used to separate ions from the solution? So these are reverse osmosis and nanofiltration. So these two membranes can remove ions from the solution. If solution is there, let's say if it contains some salt of NaCl, so it has salts here, so which is in dissolved form, so it can remove ions from the solution. Which membrane is used to separate suspended particles from water? So suspended particles can be removed through ultrafiltration and microfiltration. And it has lesser pore size than reverse osmosis and nanofiltration. Because particulates are bigger than the ions. Let me write here. Particulates are bigger than ions. And so in ultrafiltration and microfiltration, we need less pressure, less transmembrane pressure is required. Yeah. So this microfiltration, ultrafiltration are used to remove the suspended particles from water. What are the mechanism of pollutant removal in membrane? So what are the mechanisms? So the mechanisms are straining. Straining is the dominant mechanism. Adsorption is coating on the wall by small particles, and then cake filtration. Finer particles are trapped by cake, and cake act as a filtration medium. So let's see with an example. Let's say this is the pore. So this is the membrane. This is the membrane. In this membrane, particle comes here and cannot go through the core because the size of the particle or particulate matter is more. So the size is more. It is called straining. This is the first mechanism. Adsorption is like particle will absorb over the media. Sorry, near the pores. This is adsorption. And third one is cake filtration. In cake filtration, like this, there will be a layer of cake formation near the pore. This is cake, and this will cause particle to retain. Cake itself acts, what is written? Cake acts as a filtration medium. So here this is the cake. The impurities which are trapped over the pores. So this is the cake. So cake itself acts as a filtration medium. The term, which term? The term is used to describe a complete unit comprised of the membranes. So if there are multiple membranes, let's say these are hollow membranes, so they are packed together because a single unit may not be able to satisfy the water demand or whatever we need. So these membranes are multiple membranes are packed into a one unit, and these are called modules. So the term module is used to describe the complete unit comprised of a membrane. This is called module. What are the principal types of membrane modules used in wastewater treatment? So what are the principal membrane modules which are used in wastewater treatment? So the question is that. So we have, so the principal types of membrane modules are tubular. It is kind of a tube. So another one is spiral wound. So a sheet is taken and it is spiral wound. Another one is hollow fiber. It is hollow. And last one is flat. So a flat sheet is taken and water is passed through that sheet. Next question is the deposit of retained material. The deposit of retained. The deposit of retained material that accumulate at the feed side of a membrane is called. The deposit of retained material that accumulate at the feed side is called membrane fouling. So what happens after the operation? Like if it is organic matter, so it will retain over here. It will retain over the pores, near the pores, and it may clog also sometimes. Plug. So this is called membrane fouling. The deposit the deposit of the retained material that accumulate at the feed side. So this is the feed side. This is the feed side. So the deposit of the retained material that accumulate at the feed side of the membrane is called membrane fouling. So this phenomena is called membrane fouling. So membrane fouling can be caused by. So what are the reasons for membrane fouling? What are the reasons? So the reason is like one is the particulate matter. if particulate matter will, suppose this is the membrane, if particulate matter will come, they will clog the membrane like this, with particulate matter. Another one is dissolved organic matter. So dissolved organic matter may come, and like if it is organic matter, it will cause slimy layer to form. Like the layer will form, the sticky layer will form, and that will affect the working of the membrane and biological growth also. If organic matter will attach over the membrane, then biological growth may also happen. So this may cause membrane fouling. What are the effects of membrane fouling? So if membrane fouling happens, so effect is a gradual reduction in filtrate water flow. So the filtrate water which we are getting, filtrate water means permeate. Filtrate water is nothing but permeate. So the permeate, gradual reduction in permeate water flow rate at constant pressure. So if we are providing the constant pressure, let me see if there is an issue in the PPT. Slide number 13. So what are the effects of membrane fouling? So membrane fouling we understood. So what are the effects we want to? So if we have constant transmembrane pressure, if we have constant transmembrane pressure, then there will be gradual reduction in the filtrate water, because head loss will be more because head loss will be more, because more surface area is there, that will cause more energy, more head is required, so that will cause gradual reduction in filtrate water flow. And if we want to maintain constant flux, if we want to constant flux, then we need to increase transmembrane pressure. Like we have studied in the filtration also, constant head, constant constant head, and uh, constant flow conditions. So if we so for constant head condition, we should apply constant head. This water depth above the filter bed is uh, water depth above the filter bed is maintained constant, but with time what we observe is like our flow rate or discharge coming out of the filtration bed decreases, because as the filtration process proceeds, the particles or particulate matter will get accumulated over and under the filter media, and because of that, the head loss increases because of more surface area will cause more head loss to occur. So if more head loss occurs, the discharge reduces, provided the head loss is constant, so the discharge decreases with time. So after a certain time, we do backwashing and all. So likewise, here also the same concept is used. So if the head loss reduces, we clean it. So let's proceed further. What is irreversible membrane fouling? So the thing is that we uh, clean the membrane, and sometimes what happens, the cleaning is not the cleaning is not the cleaning will be done, but it will not make the membrane as it was initially. So there is some kind of uh, loss. So in that case, we study like what is irreversible membrane fouling. So when the fouling cannot be reversed as it was earlier, so this is called irreversible. Let's understand. The fouling is termed irreversible if the loss in flux cannot be recovered by backwashing and cleaning operations. The flux which we used to get earlier, flux is not the same. Flux is not the same which we used to get, which we used to get initially. So the flux actually what will happen? So the flux will not increase. So the most cases the flux will decrease. What are different types of membrane fouling? So let's understand the different types. So first one is pore narrowing. Pore narrowing, as the word states, pore narrow. The pore which has a width of initially let's say x. So after the fouling, before it has pore width, let's say it was x. So pore width finally it will be x minus delta x. So the pore is getting narrow and narrow with filtration process. So this is pore narrowing. Another type of membrane fouling is pore plugging. Pore is plugged with the particulate matter. During filtration, a particle comes and it will plug the pore of the membrane. So this is called pore plugging. So this will cause fouling. And another one is third one is gel formation. So what will happen when we pass the water? So gel will form over the pores. This is gel. So this is called gel formation. So we have three types of membrane fouling. One is pore narrowing. Pore is getting narrowed down, and then pore plugging, and then gel formation. The gel will form or the cake will form over the pores, so that which will reduce the ultimately there will be reduce in the flux. Membrane fouling means ultimately it will reduce the flux. That's it. And what is flux here? You will study about that thing in the last two questions. How membrane fouling can be controlled? So if membrane fouling is there, so we need to clean it and we need to control it. Let's see. There are three ways of controlling the membrane fouling. So first one is membrane backflushing. Like in filters, it is similar to filtration process. So like in filter, we used to do backwashing. So here what we are doing backflushing. It's not backwashing, it's backflushing. Backflushing. It's backflushing. So backflushing is done to eliminate the accumulated materials from the membrane surface with water and or air. So the water individually or with in combination with air or air individually or in combination with air can be used for backflushing. And another way is chemical clean. Another way is chemical cleaning of membranes. So what is chemical cleaning? We use some chemicals that we'll discuss in the next question. What are those chemicals? Chemical cleaning of the membranes. So these are used to remove the constituents that are not removed during the conventional backwashing. So what will happen if something is not removed during membrane backflushing when we are applying water and air? If something is not removed, then we have to use then we have to use some chemicals and these chemical constituents that we'll study in one more MCQ is there. So then we use chemical cleaning of the membrane. And another one is this is not a correct means third one is not proper, but what can we do? So initially two are cleaning mechanism when it is clogged, when the membrane is fouled, when membrane fouling is done. Third one is kind of preventive measure. So, like how we can control the membrane fouling. So they are saying like we need pre-treatment of the feed water. So if we pre-treat the feed water, we can up to some extent we can prevent the membrane fouling. So it's a preventive measure. So they are asking to pre-treat the feed water so that membrane fouling can be controlled up to some extent. Pre-treatment is used to reduce the total suspended solids concentration and bacterial content from of the feed water. So it's a kind of preventive measure. So the first two measures we have to take after first two measures we have to take when membrane fouling has happened, and third measure we have to take before the membrane fouling because it is a preventive measure. Give some name of some usual cleaning agents for cleaning agents uh, for this is for membrane fouling. So what are the some usual cleaning agents? These are acids. So acids can be used for cleaning. Alkaline solutions can be used. Oxidizing compounds can be used because we studied like there will be bacteria. So like we have seen it in this thing. Biological growth. So biological growth may happen. So if biological growth happens, we'll apply oxidizing agent. So it will oxidize the biological microbes or yeah. Complexing agent will reduce the solubility, will increase of the solubility, and it can easily pass through. Anti-precipitant. So those particles which can precipitate, we will solubilize them, and we will solubilize solubilize them, and then so that the fouling will not happen, cannot happen. Detergents, they are used for cleaning. We are aware of that. So these cleaning agents can be used for cleaning the membrane. Now we have the question. So the question is, the membrane has a thickness of 75 micrometer. So here we can learn many things in this question. So the membrane thickness is, see the thickness is, membrane thickness is 75 micrometer. The membranes are very thin, and the requirement is like they should have some strength so that they can take the pressure applied by and the pressure which we apply, like transmembrane pressure which we apply, they should be able to take that pressure. The membrane has a thickness of 75 micrometer, and the porosity is not and the porosity of 0.38. porosity porosity is 0.38. Porosity is 0.38. Pure water flux of the membrane is 36. Flux is 36 meter cube per meter square per hour, and pressure drop of 1.4. Need to check. So it has a flux of 36 meter cube per meter square. 36 meter cube 36 meter cube per meter square per hour. And pressure drop of 1.4 bar. Is it reflecting here? The flux is 30 second. I think it is working fine. Flux is 36 meters square per meter square. If we convert it in the required unit, it will be 36 divided by 1 hour has 36 minutes and 30 seconds. So it will be 3600 meter cube per meter square second. 36 meter cube per meter square. Okay, so the pressure drop is 1.4 bar. Pressure drop is 1.4 bar. And average pore size that's estimated as 1.25, 1.2 micron. Pore diameter 1.2 micrometer. Calculate the value of tortuosity factor. Yet to find, it is in different color. We have to find tortuosity factor, that is tau, and we have to find resistance to the flow offered by the membrane, that is actually Rn. It is Rn. And the viscosity is given as 0.9 centipoise. 0.9 centipoise. We will start this question. Pressure drop is 1.4. Okay, correct. Dynamic viscosity. Dynamic viscosity is 0.9 centipoise. Pore dia is 1.2 micrometer. 1.2 micrometer. And pore radius, because we will be using radius here. So pore radius will be 0.6 micrometer. And we need to find tortuosity. What is this? TOR, TOR, TUSI, TOR, TUI, TOR, TUSIT. Tortuosity, that is tau and Rm. We need to find these two values. So we should be aware of two things. Thickness was how much? 75. Okay. This is the same question. I'm going to delete this. So we have the formula here. J is equals to Q4 epsilon divided by A. J is nothing but the flux through the pore. These are three terms actually. Let me rewrite it. J is equals to Q rho of 4 Q into rho of 4 into epsilon divided by A. So if we expand this formula, we will get epsilon pi r to the power 4 delta P, that is pressure drop, divided by 8 mu tau delta Z. This is the thickness. This is the thickness. This is the pressure drop. Thickness. This is the pressure drop. Last thing we know, tau is tortuosity. J is the flux. So we need to find tau from our equation. Pi r to the power 4 delta P divided by 8 mu tau delta Z from here. And this r is the pore radius. So we need to calculate tau from this equation. Epsilon pi r to the power 4 delta T divided by 8 mu J delta Z. So epsilon we know it was 0.38, pi will be pi, r will be 0.6 into 10 to the power minus 6 to the power 4. Del pressure drop was how much? Pressure drop was 1.4 bar that we have to convert into Pascal. So 1.4, we'll write in different font color. 1.4 into 10 to the power 5 Pascal. And this also we have to convert. mu is the viscosity. That will convert by multiplying 0.9 into 10 to the power minus 4 kg per meter second. So this is nothing but Pascal second or Newton second meter square. So it will be this point. And what else to change? Yeah, this much. So if we solve this 0.38 pi into 0.6 into 10 to the power minus 6, pressure drop is how much? Was 1.4 into 10 to the power minus 5. 1.4 into 10 to the power plus 5, not minus 5. Yeah, 10 to the power plus 5, and then 8 what is dynamic viscosity? It is 0.9 into 10 to the power minus 4, correct? Into J was 36 divided by 3600. Let's check per second. Yeah, correct. 36 divided by 3600. And what else? Delta Z. Delta Z was the thickness of the membrane. Delta Z was how much? 75, I think. Yeah, it will be 75 into 10 to the power minus 6 meter. So the value of tau will be, let's calculate. It will not be 0.9, it will be 9. Consider minus 20. So into simplify. There is something issue in the formula also. Let's cross check it again. It should be square. Should be square. So now if we calculate, epsilon pi r square delta p 8 mu. So if we solve it, we'll get tau is equals to 3.55. Formula is like, the pi is not here. epsilon r square delta p divided by 8 mu tau delta z. So that pi we have to remove, this pi also and this pi also, and then if we solve it, let's check. We'll solve one more question. So in this question we will have, so what will be the change in flux? What is the change in flux when temperature changes from 16 degrees Celsius to 24 degrees Celsius? In previous question we missed one more part. We'll solve that first. So here the second part is to calculate Rm. The formula for Rm is, like, we calculate Rm from this formula: J is equals to delta P divided by mu Rm. Rm will be delta P divided by mu into J. So Rm will be, delta P was 1.4 into 10 to the power 5 divided by mu was 9 into 10 to the power minus 4 into J was 36 divided by 56 centimeter. So if we solve, the value of iron comes out to be 1.55 into 10 to the power 10. It has a unit of meter inverse. So we need to calculate what is the change in flux J when J was 16 and when J will reach 24 degrees Celsius. So what is the change in the flux? So what all the data we have here? Let's see. So the flux is given by, J is given by Q by A. We can write it as delta P by mu Rm. So J, we know that it is volumetric water flux through the membrane. So it has a unit of meter cube per meter square per hour or meter per hour. Q is the volumetric flow rate of pure water. Q is in meter cube per hour. And A is the surface area of clean membrane. A is the surface area of clean membrane. And delta P is transmembrane pressure. In kPa. Mu is dynamic viscosity. Unit is Pascal second. And then Rm is membrane resistance coefficient. So we know that the viscosity is changing with temperature. So the relation of viscosity with temperature is given as we studied in the initial MCQs also. Mu will be 1.777 minus 0.052 T plus 6.25 into 10 to the power minus 4 T square. So this is the temperature. T here is temperature in degrees Celsius. So first we want to calculate it for 16 degrees Celsius. It will be 1.777 minus 0.052. T is temperature is 16 plus 6.25 into 10 to the power minus 4 into 16 whole square. So this we have to calculate, and we have to calculate at 24. We are calculating at 24, 25, 24 we will calculate, not 24. 24 also 1.777 minus 0.052 into it will be 24 degrees Celsius plus 6.25 into 10 to the power minus 4 into 24 whole square. So this value is coming out to be so the unit of this equation, if we get the value will come out in millipascal Pascal second. Millipascal second. It here Pascal second. Millipascal second. If we solve this first. Millipascal second. So yeah. Now we need to check what is the change in the flux. We need to find what is the change in the flux when temperature changes from 16 to 24 degrees Celsius. Formula of J is delta P divided by mu Rm. So this will be constant. So J at 16 will be delta P divided by mu at 16 Rm. J at 24 will be delta P divided by mu 24 into Rm. Now we need to calculate if I divide J24 divided by J16, come out as delta P we will get it as divided by J16 is equals to it should be 24, it should be 16. So what is mu16? Mu16 value is 1.105. This will be 1.889. J24 divided by J16 will be, the ratio will be 1.24. So what can we say? J24 divided by J16 is equals to is equals to 1.24. So we can say the flux at 24 degrees Celsius is 1.24 times flux at 16 degrees Celsius. If you want to say, if you want to calculate percentage increase in flux, then it can calculate as J at 24 minus J at 16 divided by J at 16. So how will we calculate? So it will be J at 24 will be 1.24 of J of 16 minus J of 16 divided by J of 16. So it will be 1.24 minus 1 divided by it will be into 100. This will also be into 100 into 100. So increase will be 24%. So the flux, so as the temperature increases, the flux will increase according to the equation. This equation we use here. This equation we use here. And with the temperature, what is happening? With temperature, the viscosity is decreasing actually. With the temperature, with the temperature, fluid viscosity is decreasing. Fluid viscosity is decreasing, as you can see. And with the because of this decrease in viscosity, the friction is getting there will be less friction, and because of that, and the flux is increasing. So this is the conclusion of this question. So this is about today's lecture. So we studied about what is the membrane is governed by the pressure force, and then about this microfiltration, reverse osmosis. Reverse osmosis is very less pore size, so more pressure is required, and this is the dynamic viscosity is Pascal second, and the unit of tau is tortuosity factor has no dimensions. This is the relation we studied, and we studied about what is membrane, what are the inputs, and we studied about feed stream, product stream, reject and concentrate. Ions can be removed through RO and nanofiltration, while the particulates can be removed through ultrafiltration and membrane filtration. And the mechanism of pollutant removal is straining, adsorption, and cake filtration. And the module is a term which is used for the unit which consists of number of separate number of individual membrane units. This is called module. So these are the types of membranes which are used in water and wastewater treatment. So like the feed side, there is some accumulation of uh, some material, some retained material. It is called membrane fouling. So this can be due to particulate matter, dissolved organic matter, and some biological growth also. So like what are the effects of membrane fouling? We studied like infiltration. We discussed constant head and constant flow. Likewise, irreversible is when after cleaning also some flux will change. Then the flux will not be equivalent to the initial. The flux is not equivalent to what it was initially. So there will be some decrease in the flux. So then we say it is irreversible membrane fouling. And what are different types of membrane fouling? So we studied like these are pore narrowing, pore plugging, and gel formation. So how membrane fouling we have studied like back flushing can be done, and if back flushing is not able to remove, then we will provide chemical cleaning, and then one preventive measure we have done is we need to have pre-treatment of field water so that we can reduce TSS concentration, that is total suspended solid. Yes, write it here. Total suspended solid. So if we can reduce the total suspended solid concentration and bacterial content, so our fouling can be controlled up to some extent, but we cannot assure that it will not happen. So it is a preventive measure. Cleaning agents we studied acid, alkalines, detergents, anti-precipitants, complexing agents. So this will help cleaning the membrane. So we studied about these two questions. So this was all about week 9. Thank you.